Hey guys, welcome back. In this video, we got Lewis acids and bases. So when you think of Lewis here, there we go, this guy. All right, when you think of Lewis, I think of electrons. And so we're going to look at this from the viewpoint of electrons. So our first acid and base, it was just the hydronium and hydroxide, solvent cation, solvent anion. That was our first definition with Arrhenius. Second definition with Bronsted-Lowry was a proton donor, right, and proton acceptor. Acids were proton donor, bases were proton acceptors. All right, so we had Arrhenius, acids, solvent, cation, base, solvent anion. All right, and that makes sense. Then you had Bronsted-Lowry, where you had acid was H plus or proton donor, and the base was an H plus or proton acceptor. Lewis. So its acid is an electron pair, right, acceptor. And the Lewis base is the electron pair donor. All right? And so we're looking at it from the opposite way than we did Bronsted-Lowry. Bronsted-Lowry was past the electron, or past the protons. We're talking about the electrons and how the electrons are moving, okay? All right? And so, just so you know, note, before we even get examples, hydronium is always an acid, and hydroxide is always a base in our class, which is still just in our class, or in Gen Chem 2, it's still a big statement because we don't like to say always and never in science, right? So for us, it's going to be a big deal. That's a big deal, right? So if you see hydronium, acid. If you see hydroxide, base. Doesn't matter the definition, how we're defining it, okay? All right? Okay, so you got three definitions here, right? And so we got to be very particular in what we say, okay? So I use this analogy in class. So I'm asking the acid, right? I can ask for a different thing, right? I can ask for which one's producing hydronium, which one's giving up the proton, or which one's accepting an electron pair. I ask for a base, right? I got more than one thing now, right? Which one's producing hydroxide? Which one's accepting the proton? Which one is donating the electron pair, right? So all those are relevant, okay? All right. And so for an example, if we have H plus NH3, and it'll make NH4 plus. All right, we have H plus, right, which is also, right, H plus cannot be a Lewis base, can it? All right, H plus has no electrons. So if it has no electrons, it cannot be a base. All right, so this is our acid. Ammonia is our base, right? It has that lone pair on the end. And then what we call NH4 plus is the adduct, the product of the Lewis acid-base reaction. All right. Very, common example. Boron trifluoride plus ammonia going to, well, let's do it the double-headed arrow. Well, what we're going to get, BF3NH3. Well, this is the adduct. Which one's the acid and which one's the base? Well, sometimes it's helpful to draw it out. So boron, I got F, F, F. I got nitrogen, H, H, H. So we got do. All right. There's that. Well, hopefully you can figure it out really quick. Hopefully we notice that we have an electron pair right there. And so this electron pair can be donated to B. Fluorines are full, right? Fluorine has 8 electrons. Fluorine's not going to give up any electron density, and it's not going to take any more. It can't violate the octet rule, right? And so we're going to have our acid in boron. Wow. Acid in boron trifluoride. There we go. Got it out. Base in ammonia. And how this looks, right? You have your boron, your 3 fluorines, your nitrogen, and your 3 hydrogens. Now, I didn't draw this perfectly, but at the right, what we call stereochemistry, but it's good enough for our Gen Chem purposes. This is what we look. This is what we draw. All right? And right here, that's your coordinate covalent bond from the acid-base reaction. So that's Lewis acids and bases. Now, a couple things. H2O. Right? So if we look at water, HOH. Can water accept electron pairs? I don't think so. I don't think it can accept any electron pairs. It can donate. It can definitely donate. So water is only a Lewis base. In the Bronsted-Lowry definition, it can be an acid, it can be a base. But in the Lewis definition, it's only a base. And another thing, note, most metal cations are Lewis what? Are they acids or bases? Well, if you're a cation, right, you are electron poor, right? You lost electrons. So if you lost electrons, you're probably not going to be donating them. You're probably going to want to accept electrons. So most metal cations are Lewis acids. All right? So that's this generic over of our Lewis acids and bases. Hopefully that works. If you have any questions, reach out. Otherwise, we'll see you next time.